Hello, my name is Shahriar Shahriari, and this is a lecture on composition of functions. This is a general math talk, but one version of this appears in my retrolinear book on linear algebra. But this is really not a linear algebra lecture. If you have two sets, how do we define a function? A function is a rule that assigns to every element of x one element of y. Each element of x gets one element of y. That's all it is. And the way we think of a function is as a map, as something that sends things over. So we have x is called the domain, y is called the codomain, and what f does is gives you a rule for how to take elements of x and send them over to y. Every element of x needs to be assigned some element of y. Not all elements of y have to be assigned elements of x, and different elements of x could go to the same place. It's just that one element cannot go to several places. So that's what a function is. What we want to do is to combine functions to get new ones. The general idea is that we have a function from x to y, f. So f is a rule that takes things from x to y, and g is a rule that takes things from y to z. G is a function from y to z. We want to combine them and get a direct function from x to z. That new function we will call g circle f. It's just a map f followed by the map g. So here's the formal definition. You have x, y, and z three sets. F from x to y and g from y to z are maps. When we say maps, that's the same as functions. Then we define a new map, g circle f, from x to z, defined by g circle f of x. That's the same as g of f of x. You apply f to x, f of x, and then you apply g to the resulting thing. And this happens for every x in x. You get something in z because f of x gives you something in y, and then g of f of x being in y, will be something in z. This function is called the composition of f and g, and sometimes we just write gf for g circle f as the name of the function. The way we think of it is x and y are sets, as is z, and f is a map from x to y, g is a map from y to z, and then g circle f goes from x to z. How does g circle f work? If you have something in x, what's the rule? How do you go from x to z? You take that alpha, apply f to it, and you get something in y, then apply g to the resulting thing, and you get something in z. In algebra, we say that this diagram commutes. Doing f and then g is the same as doing g circle f. Here's an example from pre-calculus. If you have a function cosine of x, r is the domain, r is also the codomain, and I've defined another function from r to r, which is g of x, x cubed minus 2x plus 1. Now, g circle f means do f first, then g. So g circle of f of x is g of f of x. Instead of f of x, I put cosine of x and get g of cosine of x. And when I plug in cosine of x into x for g, I get cosine cubed minus 2 cosine plus 1. So g circle of f of x is this function, the function that takes x and gives you cosine cubed x minus 2 cosine plus 1. Likewise, you can also define f circle g. F circle g, f of g of x means you do g first, then f. G of x is x cubed minus 2x plus 1. You take that x cubed minus 2x plus 1 and plug it in wherever you see x in the rule for f of x. And so you get cosine of x cubed minus 2x plus 1. But functions could be more complicated. F going from r to r defined by f of x sine of x. But now I can have a function g that goes r to r2, the two-dimensional plane, that's given by ex comma 1 over x squared plus 1. Plug in an x value and you get two numbers, and that's going to be an element of r2. Here, you can define again g circle f, do f first, and then follow that by g. G circle f at x, just like before, is g of f of x. F of x is sine of x, so that's g of sine of x. Now, wherever you see an x in g of x, you plug in sine of x, and you get e to the sine of x, 1 over sine squared plus 1, a function that you plug in a number in r, and you get something in r2. Here, f circle g is not even defined, because the codomain of g, where g lands, is not the same as the domain of f. If you try to do g and then f, that doesn't work, because when you start with g, you end up in r2, and then f doesn't know what to do with elements of r2. F, all it knows what to do is with elements of r. So let's make sure we're comfortable with the notation. So g circle f is just the name of one function. We could call it Fred if you like, but that's the name of one function. Often, to emphasize that it's just one function, we enclose it in parentheses. So you might see expressions like parentheses g circle f parentheses closed of x, and that just means the function g circle of f applied to x. And then remember that g circle f, even though we write g and then f, it's really f followed by g. It's really g of f of x. And g of f of x, what applies to x first is f. F is the thing that you apply to x first, and then you apply g to the result of that. When you want to do g circle f, the codomain of f, where elements of x, the domain land, has to be the same as the domain of g. The picture you have in mind is this, that y, which is the codomain of f, has to be the same as the domain of g. A couple more examples. Here's an example where f is a function from R3 to R2 and g is a function from R2 to R3. Here their definition. F takes a three tuple, three numbers, elements of R3, that's the three-dimensional space, and gives you this element in R2. Alpha, beta, gamma goes to alpha squared plus beta and 5 gamma. And G takes elements of R2 and gives you elements of R3. You take alpha, beta, and you get alpha minus 2 beta, 4 beta, and 2 alpha plus 5. These are both well-defined functions, rules that takes you from R3 to R2 in one case and R2 to R3 in the other case. We could actually combine these in two different ways. We could do F first, then G. F takes elements of R3, gives you R2, and then G follows that with taking elements of R2 and giving you something in R3, and that would be G circle F. On the other hand, if you do G first and then F, you get F circle G, and you're going from R2 to R3, then back to R2. You should stop this video, do it yourself, and then check the answer. G circle F is a map from R3 to R3, and how do I find it? I take G circle F, I have to tell you what it does to a typical element of R3. What does it do to alpha, beta, gamma? G circle F of alpha, beta, gamma is G of F of alpha, beta, gamma. F goes first. F is being applied to alpha, beta, gamma, and I know what F does to alpha, beta, gamma. It gives me alpha squared plus beta and then 5 gamma. So now I've got to apply a G to that. How do I do that? The first coordinate is alpha minus 2 beta. That means you take the first coordinate of what you plugged in minus twice the second coordinate. So that's what I do. I take this first coordinate, alpha squared plus beta, minus twice 5 gamma. What is the second coordinate you're getting? 4 beta. That's 4 times the second coordinate of what you plugged in. So 4 times 5 gamma is 20 gamma. And then the last one is 2 alpha plus 5. You take the first coordinate of what you plugged in, multiply it by 2, and add 5 to it. So you multiply alpha squared plus beta by 2 and then add 5, and you get this. Now with the same functions, I could go the other way around. I could do F circle G, which says apply G first and then F. F circle G of alpha beta. Why is it alpha beta? Because F circle G starts in R2 and ends in R2. So I'm going to give it a typical element of R2 and see where it goes. That way I know what this function is. And F circle G of alpha beta is F of G of alpha beta. So here, again, I plug in alpha beta into G, and I know exactly what I get. I get alpha minus 2 beta, 4 beta, 2 alpha plus 5. But then I've got to plug this into F. Well, how do I do that? Well, I go back to the rule for F. What's the first one? It says alpha squared plus beta. So that means the first coordinate squared plus the second coordinate. So alpha minus 2 beta is the first coordinate of the input. I square that and add that to the second coordinate, which happens to be 4 beta. And for the second entry, I have to take the third coordinate of the input and multiply it by 5. So I take these 2 alpha plus 5 and multiply it by 5, and I get 10 alpha plus 25. What we want to do now is to ask the following question. If we compose two functions, are there properties of the individual functions that are reflected into the properties of the composition? Does the composition inherit any properties from the two functions? And the answer is that in some cases, yes, in some cases, no. But we are interested in one-to-oneness and on-to-ness. Let me remind you what that is. If you have a rule that tells you sending points x into y, then if it happens to be that some point in x is sent to multiple points in y, then you don't have a function. That's what the definition of function is. On the other hand, if 2 points go to the same point, then the function is not one-to-one. A one-to-one function is a function that different points go to different places. No two different points go to the same place. Sometimes these two things are confused. A function is something that does not send one point to several points. A one-to-one function is a function that does not send two different points to the same point. And a function is not onto if there's something in the codomain in y, something like delta, that's not hit by anything. That's not at the image of any point in x. So to be onto means that everything in y is the image of something in x. The first thing we want to prove is that if you have a one-to-one map and then another one-to-one map, and these two maps share a codomain and a domain, so f goes from x to y and g goes from y to z, then the composition will also be one-to-one. The composition of two one-to-one maps, as long as you can compose them, is going to be a one-to-one map. The basic idea is pretty straightforward. We have this picture. If you have 2 points alpha 1 and alpha 2 in X, could they go to the same point gamma? If they did, then G circle F would not be 1 to 1. But the point is that F is 1 to 1. So these guys go to different points in Y, and those two different points have to go to the same place because this is function composition. But if that's the case, then G will not be 1 to 1. And so if F is 1 to 1 and G 1 to 1, F sends things to different places, G sends them to different places, so must G circle F. That's the basic idea, and that's basically the proof. If you want to write that down formally, the way we prove one-to-oneness is we assume two things did go to the same place. If you assumed originally that those two things were different, then we would have to get a contradiction. But usually we don't actually assume that. We just assume that we have 2 points, they go to the same place. We reserve judgment whether or not those two original points were the same or not. And then what we prove is that actually they were the same. And if we can do that, then we have shown that the map is 1 to 1. 2 points go to the same place, but then we show that can't happen unless the 2 points were really the same point. So assume that G circle F send alpha 1 and alpha 2 to the same place. We want to show that alpha 1 equals alpha 2. What is G circle F of alpha 1? Well, that's G of F of alpha 1. G circle F of alpha 2 is G of F of alpha 2. These two things are the same. This means that G of F of alpha 1, think of that as an apple, and G of F of alpha 2, think of that as a strawberry, are the same. G of apple is the same as G of strawberry, but G was 1 to 1. That means that this apple and strawberry must have been the same thing because G couldn't have sent two different things to the same place. That means F of alpha 1 must be the same as F of alpha 2, because if G of apple is the same as G of strawberry, that means G sent apple and strawberry to the same place. And a one-to-one function cannot do that unless apple and strawberry are the same. Now we look at F and we say, well, F is sending alpha 1 and alpha 2 to the same place, but F was 1 to 1, so that means alpha 1 is equal to alpha 2. And if that's the case, then we know that G circle F is 1 to 1 because we assumed that G circle F sends 2 points to the same place, but we ended up proving that those 2 points were really not different from each other. Now we do the same thing with onto-ness. If you have a map from X to Y that's onto and a map from Y to Z that's onto, then the composition is onto. The picture will tell you how the proof goes. If you have something in Z, why is it that G circle F sends something to it? So what I have to do is find you some alpha in X and convince you that alpha goes to gamma. How am I going to find that alpha? So someone gives me this gamma in Z, I have to find some alpha in X that G circle F of alpha is gamma. And how do I find that? I go the other way around. I'll say, here's gamma. How am I going to get to alpha? G is onto, so there must be some beta that hits gamma, that G of beta is gamma. And then F is onto, so there must be something in X that hits beta. So there must be some alpha that hits beta. And that alpha will be the one that will go to gamma by G circle F, because G circle F is just F followed by G. How would we write this formally? We would say pick some gamma in Z. This is an arbitrary element of Z. And I want to show you that there's some alpha in X with G circle F of alpha equals gamma. I don't know what alpha is. I've got to come up with alpha. I can't just say, well, alpha goes to beta and then beta goes to gamma. I can't say that because I don't know that. I've been told what gamma is, and someone is challenging me, saying that find me something in X that if you apply G circle F to that thing, which I'm calling alpha, ends up in gamma. I have to produce alpha. And I do that in 2 steps, just like the diagram showed before. G is onto, so there must be some beta in Y. Backward E means there exists. There exists some element beta in Y such that G, when applied to beta, gives us gamma. We're not in X, we don't have our alpha, but we're now back in Y. And then I'll say that F is onto, so there must be some alpha in X that F sends to beta. So from gamma, you get beta, and then from beta, you get alpha. Okay, so what? Now this alpha is the alpha that I want, but to make the proof complete, I have to show you that it actually has the property that I want. I came up with this alpha. Then I'll say, look at G circle F of alpha. The proof of the pudding is in the eating. Let's see if we get gamma or not. Well, G circle F of alpha is G of F of alpha. And F of alpha is beta, and G of beta is gamma. And so G circle F does send alpha to gamma, and therefore the map is onto. Because we started with an arbitrary element gamma in Z, we found some element alpha in X that had the property that when we applied G circle F to it, we got gamma. I can combine the 2 theorems that I have. If you compose 2 one-to-one maps, you get a one-to-one map. If you compose 2 onto maps, you get an onto map. What I have now is that if you compose two bijections, the bijection is a one-to-one onto map. If F is one-to-one onto and G is one-to-one onto, then the composition will be one-to-one and onto. Why? Well, because we just proved that if both of them are one-to-one, the composition will be one-to-one, and if both of them are onto, the composition will be onto. As an example, F, a map from 1, 2, 3 to 1, 2, 3, 1 is going to 2, is going to 3, and 3 is going to 1, and G is this other map from 1, 2, 3 to 1, 2, 3, 1 goes to 3, 2 goes to 1, 3 goes to 2. Both of them are one-to-one and onto. Everything is hit, and no two things go to the same place. So these are bijections. If we compose them, doing F first, and then G, this is G circle F, and you see what we get. Where does 1 go? Well, 1 goes to 2, but then ends up in 1. So 1 is going to 1. Where does 2 go? 2 goes to 3, but then it goes to 2. So 2 is going to 2. Where does 3 go? 3 goes to 1 to 3. 3 goes to 3. So 1 goes to 1, 2 goes to 2, 3 goes to 3, and that's the identity map. So these two bijections, when you compose them, you get the identity map. We say that these two functions are inverses of each other. Inverses is the subject of the next video. This is the end of this lecture. Like my video if you liked it. Subscribe to my videos if you want to be subjected to more undergraduate math videos on your feed. Keep hydrated at all times.